The next is about instruction set of 8085 microprocessor. So what do you mean by instruction set? Instruction set is a group of commands for a CPU in a machine. Okay, the machine what we are using is 8085. So it is a set of commands to do a particular job. We are going for instruction set, and instruction set can be classified into 5 categories under 8085 microprocessor. They are data transfer instruction, arithmetic instructions, logical instructions, branching instructions, and control instructions. So the first instruction is data transfer instruction. So these are the instructions which copies the content of the source register to the destination register. I have already given some examples when I am taking addressing modes. So we can see one by one now. So here MOV RD, RS. So RS specifies the source register, and RD specifies to destination register, right? So now with the help of MOV stands for move operation. MOV, it stands for move operation. So now the content which is present in the source register is moved towards the register D, that is destination register, at the end of MOV RD, RS operation. Similarly, the next instruction says MOV M, RS. The content which is present in the source register is moved to the memory pointer, that is M. M stands for it indicates HL register. Right, the data which is present in the source register is moved to the HL pair at the end of MOV M, RS instruction. So the next one is about MOV RD, M. The memory, it contains an HL pair. HL pair, it contains an address. That address, it points to a data. That data which is present in that particular address is moved towards the destination register at the end of MOV RD, M instruction. So for this I have explained already in indirect addressing modes, right? So these are some set of move instructions. The next one is for data transfer instruction. The next one is MVI instruction. So MV, it stands for move, and I stands for immediate, and I stands for immediate. So move immediate R, data. The data will be specified directly, and the data is moved immediately to any one of the register. So I have given the example here. Let's consider 60 to be the data. That data 60 is moved towards the register B at the end of MOI B, 60 instruction. Okay, the data can be also moved to the register which is pointed by the memory pointer with the help of HL register. If this is the case, let's say MVI M, 05. If this is the data, at the end of this instruction, the data can be moved to the register pair HL, where this memory points to the register pair HL. So at the end of the operation, H, it doesn't have any data. The data will be moved inside the register, L register alone. Okay. If it is more than 16-bit data, then this H register can be occupied with those which cannot be fixed with 8 bit of lower register. Okay, so the next instruction is LDA. LD it stands for LD stands for load and A stands for accumulator. A stands for accumulator. So load the value of accumulator, the content of accumulator. Load the content of accumulator. So now LDA 2050, the content which is present in the memory location is loaded in the A register. Okay, so the content which is present in the memory location will be loaded in A register at the end of LDA 2050 operation. So here LDA 2050, LDA 2050 is the address. That address, it points to a data or a content. That data will be loaded to the accumulator A at the end of LDA 2050 operation. The next thing is, which is similar to the load operation, but LDAX. So here the letter X, it specifies register pair. LDAX, X specifies the register pair. Okay, so it says that loading the content which is present in D, or it loads with the content of memory location whose address is specified by BC or DE pair. So here we are, for example, we are using register D. So if you are specifying register D, then if it comes with X also, if there is X symbol, that means it is not coming with D alone. It comes as a pair, that is DE pair, or even it can be a register pair also. Okay, so it loads the content of the memory location whose address is specified by DE pair. So at the end of LDAX operation, what happens? D and E, it points to a address value. Let's say the address value to be 4000, right? The 4000, it contains a data. That data will be loaded to the accumulator at the end of this operation. So here we have STA 16-bit address. So the meaning of STA here is ST, it stands for store the value of accumulator. A stands for accumulator. So at the end of this instruction, STA 16-bit address. STA, the 16-bit address, the example of 16-bit address is given to, that is 2000H. So stores the data from the accumulator to the 16-bit address. So at the end of this operation, the accumulator value, let's say the value of accumulator is 8. At the end of this instruction, that data 8 is moved to the register which is pointed by the instruction. The instruction is pointing the register address 2000. So at the end of this instruction, the data 08 will be moved to the specified address. So before execution, the value is present in the accumulator 0A and the address 2000 is left empty. After execution, it says the value which is present in the register 08 is moved to the specified address 2000. Okay, right? So this is for STA 2000H. Similarly, for SHLD, you are using the register pair. Okay, you are using a register pair, that is it stores the data from the register pair to the 16-bit address. Okay, so the register pair SHLD 2500H means it is indicating the register pair D. D always comes with the register pair E, right? So the content which is present in the register pair is moved to the specified address location. So what does this content contains? DE contains a data. Let's say the data to be 4100. Okay, so that data is stored to the specified address location 2500, right? So even these locations can carry only 8-bit of information. So 2500, it carries the information of the E register, and 2501, it carries the data of the D register. Okay, so it stores, you are storing the content which is present inside any register pair to the specified address location. Okay, since if it is more than 8-bit, register pair means it is 16-bit, so that each register it has only 8-bit. So 8 bits the data can be moved to the first address 2500, which is pointed from the program, and then 2501 will be updated with the register D, higher order address, I mean higher order data, right? So after that, the next kind of instruction is XCHG, which stands for exchange register pair with the specified register, with the indicated register. So for example, exchange the register pair with D. So register pair here, it talks about HL. HL register pair, it contains a data before execution. HL register pair, it contains a data. Let's say the data to be 4010, and we are talking about pair, register pair register. So that means it comes with DE. It doesn't comes with D register alone. It comes with DE register. So DE will be having some other value. Let's say the value to be 8020. So after executing this address, after executing, HL register will be updated with the value which is present in DE. DE is what? 8020, and DE register will be updated with the value which is present in HL, that is 4010. So the next instruction is IN instruction, that is input, from the input IN 80H. Okay, so copy the data to the accumulator. So this IN80H 80, it points to an 8-bit address which has a data. Let's say the data to be 01. At the end of the instruction IN80H, after executing IN80H instruction, what happens? The content which is present in the given address 80 is moved to the accumulator. Accumulator is loaded with this address. Similarly for out 50H, right? The address 50 will be kept empty before executing this out 50H instruction. So after executing out 50H instruction, the content which is present in the accumulator, let's say the value to be 02, is loaded to the specified location 50. So at the end of this out 50H, 50 is the address. That address, it points to a data which is moved from the accumulator. So the next type of instruction is arithmetic instruction. These instructions are used for performing arithmetic operations such as addition, subtraction, multiplication, division, and also for increment and decrement and comparing operations. So first we can see some addition operation and subtraction. So ADDR. So ADD stands for addition, R is for a register. So the example is add B. The content which is present in the B register is added with A. The result is stored back in A register. Okay, the content which is present in B register is added with A and the result is stored back in A register. For example, the content which is present in BB3, A is 1 and together it forms number 4. The next addressing mode is ADI followed by the data. Okay, so ADI, let's say the example to be ADI 10. So at the end of this instruction, the immediate data 10 is being added with the content which is present in the A register and the result is stored back again in A register. Let's say the content to be 2. So 10 plus 2 will be 12 at the end of this instruction. Next is about DAD register pair. The example is DAD. So this happens, the addition happens between two register pairs. If I have specified the register to be D register, so DE pair, it has a data as well as HE. This is being added with the memory pointer HL pair. So DE, let's say the data is to be 05 and 04. Here let's say the data to be 03 and 02. So the addition operation, it happens between these two registers. The higher order registers are added separately and the lower order registers are added separately. So at the end of this operation, the high shell pair will be updated with the addition, the result of addition. So height will be having 0 plus 5 is 08 and 4 plus 2 is 06. At the end of this DAD instruction, the HL pair will be updated with the addition instruction. The subtraction operation is similar to that of the addition operation. We have two examples here. SUB B. That means at the end of this instruction, the content which is present in the register B is subtracted with the content which is present in accumulator register and the result is stored back in accumulator. Let's say the content be 8 in accumulator. It is subtracted with the data 6. 8 subtracted with 6 will give you 2. Similar thing is for SBI, the data 25H, the next example here. So here the content which is present in the accumulator is directly subtracted with the data. Let's see the content which is present in the accumulator is 50. At the end of this instruction, the accumulator value will be loaded with 25. Okay. The next instruction is incrementing and decrementing instruction. At the end of this instruction, the content which is present in the register can be either incremented or decremented by 1. So the example is INR B. It says the content which is present in the B register is incremented by 1 at the end of this operation. So let's say before execution the register B contains 2, means at the end of this increment operation the register B can be loaded with 2 plus 1 3 as the result of increment B. Similarly, for DCR decrement operation, before execution, if the value of D is 5, then after execution, the value is decremented by 1. That means 5 minus 1 is 4. So this suits for the register pair increment and decrement operations. So the register pair decrement or increment operation always it indicates X. X indicates the register pair. For example, INX INHD means D has the register pair DE. So let's say before execution, if the content which is present in DE pair is 2000, after executing the increment operation, the DE pair can be updated by incrementing the lower order address E from 00 to plus 1. It is incremented by 1. So at the end of operation, DE contains the value 2001. This is the similar case for DCXD. So decrement the value of D. For example, before execution, if the value is okay, if the value is 2001, means after executing the decrement operation, the value of DE pair becomes, it is decremented by 1, so it becomes 2000. For the comparison operation CMP or CMPD, the content of the register is just compared with the content of the accumulator. So here the example is the register value. The register value is D. The content which is present in the register value D is being compared with the value which is present in the accumulator, but the results are not altered. If A is less than the register value, then the 0 bit will be equal to 0 and the carry bit will also be equal to 0. If A is equal to the register, then the 0 bit will be equal to 1, 0 flag will be equal to 1, and when A is less than the register, the carry flag will be equal to 1. These are the flags which are affected due to the comparison operation.